Okay, this is our third and final reaction that we're going to cover, which takes place in aqueous solutions. Now, a oxidation-reduction reaction doesn't have to take place in aqueous solution. There are some of them that don't, and we'll talk about one at the very end of this chapter. But oxidation-reduction reactions do commonly take place in there. So in section 4.9, we're covering this section. Short name for oxidation-reduction reaction is redox reaction. Can you see why it would be called that, where they're getting the letters for that? So that's a redox reaction. I very often will call it that because it's so much more quick to say than oxidation-reduction reaction. But whether you call it one or the other, what it is an electron transfer reaction. Electrons are coming from one substance and moving to another substance and being transferred to that other substance, forming new products in the course of that process. Okay, so let's look at this reaction. This is not taking place in aqueous solution. We have the solid sodium and chlorine gas. If I were to cut off a piece of sodium, it's a really soft metal, and drop it into a flask that contains chlorine gas, it would kind of ignite, and I'm going to put that in quotes because ignition usually refers to reacting with oxygen, but you'll see this flare up that happens, gives off a lot of hot light and heat, and you end up seeing forming some sodium chloride, some salt crystals on the flask. So let's look at what's happening with the sodium, okay? Let's move to the computer screen here. It starts as sodium the element. Now when you see sodium the element, it doesn't have a charge. It has as many protons as it has electrons. It has no charge, so I'll put a 0 up here. But over here in this compound, it has a +1 charge. So it's going from no charge to a +1 charge. Okay? To do that, it has to lose an electron. You pulled an electron off of it and it gives it a positive charge. And this would be how we would write what's happening with just the sodium, forgetting about the chlorine. The sodium with no charge, there are 2 of them, is becoming 2 sodiums with a +1 charge, and it lost 2 electrons. So those electrons have been removed. Losing electrons, removing electrons, they will be written as a product, okay? Written as a product. Because they're no longer attached to the sodium, they've been removed. Now let's look at chlorine. Chlorine is starting as elemental chlorine. It has no charge. It has no charge at all, 0. That's what elements have. But over here in the ionic compound, in the ionic compound world, it has a minus, come on maybe, there you go, a -1 charge, okay? Now how do you go from no charge, maybe I can get it to work there, from no charge to a -1 charge? Well, you had to gain an electron to do that. So we could write the gaining of electron by the chlorine as each chlorine atom is gaining 1 for a total of a gain of 2. So you would write the electrons on the reactant side if it is gaining electrons, okay? And when each chlorine gains an electron, that's how you make the 2 Cl- ions. So a transfer of electrons are occurring, and we could write these reactions together as a complete reaction. Okay, so let's see if I can get my pen to work. Come on, pen. It's starting to be cantankerous. So we have our writing it together, or we could write them as what we call half reactions, where we're writing what the gain of electron and the loss of electrons. Okay, so that's what this says. These are the half reactions for this reaction. Now, a half reaction cannot occur by itself. You can't have one of those half reactions without having the other half reaction take place alongside of it, because the 2 electrons that are being gained by the chlorine, maybe I can get it to right if I keep on circling. No. The 2 electrons being gained by the chlorine are the same electrons that are being lost by the sodium. So one can't happen without the other one. Now, this reaction is called an oxidation reaction. The loss of electrons is oxidation. The second one is a reduction reaction. The gaining of electrons is a reduction. Now, I wish my weight loss program involved gaining weight, and that would be a weight reduction program. We don't usually use those words together. But what's being reduced is the charge. okay? The chlorine, as you look at it there, has no charge, and it's going down to a -1 charge, so that is a reduction of the charge and not a gaining of electrons, okay? Because the loss of electrons, I mean, it is a gaining of electrons, so the charge is going down, and that's why we call it a reduction. Now, having said all that, it sounds very confusing to me, so here's how I keep it straight. Okay, I already told you that's one way to keep it straight. If you're going to call it a reduction, it's because the charge is being reduced. And sometimes that's really handy. I'm looking for how the charge changes. If I see it going down, I know that thing was reduced. But another way is to use a mnemonic, and this is the mnemonic I like to use. Leo says grr. Leo is a lion, okay? And lions growl. So I use Leo says grr as my memory device to keep it straight. Leo, loss of electrons is oxidation. Grr, gaining electrons is reduction. Okay, so we've got those two statements. Leo, loss of electrons is oxidation. Grr, gain of electrons is reduction. I've seen students come up and say, oh, I learned oil rig in high school, and oil rig works as well, but that's not the one I've got up here, okay? And then we have to confuse it a little bit further, and we have two more terms. We have oxidizing agent. Oxidizing agents aren't the one being oxidized. Oxidizing agents are the ones being reduced. Why do we call them oxidizing agents? Well, let's think about agents that you might be familiar with. An actor will have an agent. An actor has an agent. What does that agent do? That agent enables the actor to act. The agent goes and finds jobs for them to do. Maybe it is a cat food commercial. I found a cat food commercial for you to do, you go act. Or maybe it's a star role in a big, production. But the agent isn't the one acting. So an actor's agent doesn't act. He enables the actor to act. Or a band's agent. They're not in the band. They're not playing or singing. They are enabling the band to sing. So a musician's agent doesn't do it. So oxidizing agents aren't oxidized. They are enabling the other guy to get oxidized. They are in there to help the other guy get oxidized. So how do you enable something to get oxidized? By yourself being reduced. So the oxidizing agent is the guy being reduced. Same thing with reducing agent. It's not the guy being reduced. It is enabling the other guy to be reduced. So it's the one being oxidized. So I hate that language, but it's the language that's used in the world of redox reactions, and we need to keep it straight. So when you see a reaction, you ought to be able to recognize if it is a redox reaction, if it is an oxidation-reduction reaction. So let's look at a few reactions, a few examples of redox reactions. Okay, now we've already examined this one fairly closely, but if we were just thrown this on a test and say, what kind of reaction is this? You should be able to figure out it's a redox reaction but by knowing elements have no charge, but in an ionic compound they have charges, so charges are changing. Therefore, it is a redox reaction, and we've already talked about what's oxidized and what's reduced. But let's look at this one a little more closely. Zinc, the solid, is an element. Elements have no charges. Okay? Over here we have an ionic compound in which we have copper, and I know that it has a 2+ charge. Now, how do I know that? Because I have memorized that nitrate is -1, and there are 2 of them. Now this is not, this is a charge on that ion, and it's still present here. It's not anything changing. But let's follow over to the right-hand side. Now we have zinc inside of this ionic compound with the 2 nitrates. So zinc over here has a +2 charge, and the copper is just elemental copper. It has no charge. So now we can follow and see that zinc went from no charge to a +2 charge. And we can see that copper went from a +2 charge to no charge. So now we can go through and they could say, at this point we know this is an oxidation-reduction reaction or a redox reaction. We could then go decide who's oxidized, who's reduced, who's the oxidizing agent, who's the reducing agent. So we go from a 0 to +2 for zinc. Did you gain or lose electrons to do that? Well, you had to lose electrons. So that's Leo. So what we would say is that zinc is oxidized. And if it's oxidized, it is the reducing agent. And then we could do the same thing for the copper. We went from a +2 charge to no charge. You had to gain electrons to do that. Gain is GER. Gain electrons is reduction. So we would say that the copper 2 plus, and let me write it up here, the copper 2 plus is reduced. Therefore, the copper 2 plus is the oxidizing agent. So you've got to look at the charges in order to do that. One more, all right? Here I have calcium with no charge turning into calcium in a compound with 2 OH minuses, so that's the ion calcium 2 plus, okay? And so I know with certainty if anything changes charges, that's a redox reaction. To do that, you had to lose electrons, so this calcium is oxidized in order to do that. Now it's hard to know what's happening inside of here because there are no charges on water. It is not an ionic compound. But we know elemental hydrogen has no charge. We know if something is oxidized and something else has to be reduced, so I can infer that this was reduced if the other one was oxidized. But I can't really tell that that's what's happening. So what we have to do and where we need to go next is to look at what's called an oxidation number. And in examining oxidation numbers, what we're going to do is be able to look at a substance that has no charge and assign these numbers to them, which are as if they were charged, okay? So that's what we'll do in our next lecture video.